but it still looks absolutely fine to me. So I've been halfway through my lenses lesson, not halfway through, quite a considerable amount of the way through, and looked up and suddenly realised that my number has massively dropped and therefore no one is watching. Which I can't tell you how much I did before I realised that. That's so annoying. Anyway, I've just had to watch back my video on YouTube to find out where we got to. So I will just press on, and hopefully most of you who are watching the first lesson can come back and watch this on catch up. Right, so we've put a blob of water onto some sort of carton, and people are starting to come back now. I don't know whether I should wait. I think probably most of them will have just gone because it was ages ago, wasn't it? Yeah, I'll just press on. So we've put a blob of water onto something waterproof and seen that it gets magnified, right? It gets bigger. What you've actually done there is you have made something called a convex lens out of a blob of water. So a magnifying glass is a convex lens as well. I better be a teacher and write it down because this is important. We're not going to worry too much about you memorising the words today. When you start revising, you can memorise the words. But yeah, this shape of lens is a convex lens, also called a converging lens, and I will tell you why right now, in fact. Do you remember, it doesn't matter if you don't remember, it doesn't matter if you're new, but we've talked quite a lot in these wave lessons previously about refraction. Refraction is when light slows down, so it bends. So light goes at the speed of light through space. And then when it hits things that have particles like air or glass or water, it slows down by different amounts. So we've talked a lot about how, if you imagine this is a ray of light, if you're joining me, I've only just got started again, but I'm gonna press on because this is the recorded one, so I don't want people watching on catch up. Hi, people watching on catch up in the future to get bored. So I'm just going to press on. But you haven't missed anything if you're joining me live now. Yeah, we've talked about refraction. So if you imagine that this pen is a light wave, and then it travels through, let's say, the air, it hits this thing, let's say, I don't know, it's a ruby. And what happens is the bottom of this particular light wave, let's say the lid of the pen, starts to slow down because it's hit the ruby, whereas the top is still travelling through air, it's still going reasonably quickly. So what happens is the same thing I keep saying as would happen to you if you got one foot stuck in treacle and the other foot was on the pavement. You would end up kind of going round in a circle, and the light, it bends like that. So it might help you, if you've learned a little bit about refraction already, it might help you to think of a convex lens as split up into different bits like that. Because if you know about refraction, you can say, okay, I know that when light hits the top of that lens, the pen lid is going to slow down. The top of the pen isn't going to have slowed down, so that convex lens is going to bend that ray of light like that. And whereas at the bottom, it's going to do the opposite, yeah? The top of the pen is slowed down, the bottom is still travelling quickly, so it's going to bend upwards. And this, if right in the middle, it's not going to bend either way. So that's what converging lenses do, is they make, converging means meet at a point. So if rays of light are travelling in straight lines like this and hit a converging lens, then they will converge. That one will bend that way, that one will bend that way, that one will carry on in a straight line, and then they converge at a point. And we've talked about before in other lessons, where light rays converge, that's when you see an image. Okay. I think we need to start drawing our diagram. I'm very sorry about all the technical difficulties. It didn't show me that there was a problem. So I only learned there was a problem when I noticed that everyone had stopped watching. So if you're just joining me and you were watching the previous video, you haven't really missed anything. We're just getting started with it. That was a recap. So have you got your bit of paper which has got loads of little dots on it? I thought we'd all do this together, yeah? What I want you to do is draw along with me to a certain point, and then I'll tell you when I'm going to carry on, and I want you to just stop and watch. We'll go through all the little rules. Basically, what we're going to do now is draw a diagram to show how light behaves when it hits a lens, which is incredibly cool. It's amazing that humans can predict this sort of thing. The first thing you need to do is put a line straight through the centre of your piece of paper lengthways like that. And this is going to be what's called our principal axis. Makes sense, doesn't it? you know, on graphs that we've done before, you get the x-axis and the y-axis. This is the principal axis. So just straight down the middle, you should have 4 squares. I'm going to call them squares. I know they're rectangles. You should have 4 squares on one side and 4 squares on the other side. I'm going to write principal axis. If you're just joining me, if you're watching the previous lesson, you haven't really missed anything. Just do what I do. That's not big enough, is it? You're not going to be able to see that. Can you see that? Like I say, I don't want to fuss too long about the names because you can look all this up on BBC Bite Size before you do your exam. Oh wow, that's not how you spell principal axis anyway. I'll do it bigger. Principal axis. There we go. That's the principal axis. We will draw our convex or converging lens right in the middle. Let's make it 2 squares high on either side of the principal axis. So 4 squares long altogether. So I'm just going to draw a straight line actually. And that can be our converging lens, like magnifying glass type lens. Now, it's actually shaped like this, like a sort of an eye, I suppose. If you were drawing it on an exam, how physicists draw it to save time is they just do an arrow like that and an arrow like that. So a sort of arrow pointing upwards and arrow pointing downwards, and that's your symbol for a converging lens. Okay, so there's a couple more things we need to add. I've said that lenses, converging lenses like this, convex lenses make light converge at a point. Where that point is depends on how strong the lens is. If it's a really strong lens, a really fat lens, then it would make the light converge really quickly. And if it's a weaker lens, then the light would converge further away. Where the light converges is called the focus, or principal focus. We'll say that this converging lens is going to focus our light 1 square, I know it's a rectangle, 1 square away. And we're going to label our principal focus F. So that principal focus F is where the light rays converge, yeah? And obviously it's a sort of symmetrical lens, so we'll put an F on the other side as well, because if light was coming from that direction, then that is where it was converged. I keep saying this, if you're watching live, you really haven't missed very much. We're literally just drawing this out, and we're going to start drawing our diagram soon. But I know it's not very pleasant feeling like you've started in the middle, but if you want to watch live, you can carry on watching live. Okay, and then for reasons, just for reasons basically, because it'll help us predict what the light is going to do, we also need to draw a 2F. So this is the focal length. Should we write that down? That distance between the middle of the lens and the focus is the focal length. You don't have to write it. It's all on BBC Bite Size or Save My Exams. But we need to draw another thing 2 squares away from the middle of the lens, and we'll just call that 2F. That's gonna help us when we're talking about where the objects are. So 2 squares away from the centre of the lens is 2F on that side, and it's also 2F on this side. There. Right. And that's everything we need. Hopefully follow that. If you're watching live, you could just copy out this diagram onto your square bit of paper and you haven't missed anything. Now, what we do is, what we kind of did downstairs in my downstairs toilet, is we put objects different distances away from the lens and we look at where the image forms. So what I'm going to do is I'm going to pretend that I've got an object which is exactly 2F away from the centre of the lens. And I'm going to draw a diagram to show you how you can predict what will happen to the image when the object is 2F away. Don't do it, just watch it, yeah? And then I've got 3 or 4 more that you can do as well. So you'll get plenty of time to practice, but I think it's better if you just watch. Every time I've drawn an object in these lessons, I've drawn like a cupcake or a worm. When you're drawing an actual object, you just draw an arrow pointing upwards like that. I know, it's dead boring. All our objects today are going to be arrows pointing upwards, and we're going to make them one square rectangle high, okay? So if that's my object, and I want to draw a diagram to show what happens to light rays coming off that object when they hit this lens, there's a couple of rules that I need to obey, okay? When you're drawing lens diagrams, gotta get another pen. We're going to draw 2 light rays just coming off the very top of the object, so coming from the top of this arrow, 2 light rays travelling from the object towards the mirror. Yeah, we'll keep it simple. Obviously there's loads of light rays, light's bouncing off this object in all different directions, but let's just draw 2 of them. The first one that we draw is going to go straight through the centre of the lens. And because it's passing through the very centre, it's not going to bend at all. It's not going to get refracted. It's nice and easy. It's just going to go straight through. Some of you will be thinking, but it is going to bend because it's coming out from an angle. Yeah, it bends on the way in and then it bends on the way out. So it cancels out. So don't worry about it. The first ray of light I'm going to draw, again, I think it'd be probably better if you just watched for now. I'm going to draw a ray of light going from the top of that arrow through the very centre of the lens, and that light is not going to refract. It's not going to change direction. Can you see that? Yeah. The second ray of light is a bit more tricksy. The second ray of light I'm going to draw is going to go from the top of the object again, parallel to the principal axis, which is the most physics thing I've ever said. Parallel to the principal axis. And when that one hits the centre of the lens, it's going to go through the focus. Which actually, if you've been paying attention, makes perfect sense, doesn't it? We've just said that that's what happens when light hits that bit of the lens. So I'm going to draw a straight line, ray of light travelling parallel to the principal axis. And then when it gets to this lens, the lens is going to do its job and make that ray of light travel through the focus, because that's where the light does converge. Okay. So what's happened? This is where you find out how accurate your diagram was. Really not very. Wow, what's gone wrong there? That is awful. That should have been a bit lower. Maybe that should have been a bit higher. Oh yeah, that one, it should be like that. Anyway, I'm cheating because I know what's supposed to happen. Where the light rays cross, which is clearly here, where the light rays cross, that's where we get our image, where they meet. So what has happened to this image? We've got the objects on this side, we've got the convex lens, converging lens here, and it's made light rays cross down here. Well, what's supposed to happen is that hopefully you can see that our image is now upside down. If I draw a line from the principal axis to where those rays meet, we've got an image which is upside down. And if I'd done it properly, you would be able to see that it's also, this image here, is exactly the same size as our object. It's one rectangle high. So it's inverted, it's the posh physics word for upside down. It's the same size, that's the posh physics word for being the same size. And it's also real. If an image is real, it means it can be projected onto a screen. So if you imagine that this is our candle and this is our magnifying glass, this image would get projected upside down on the screen. So it's a real image, but you'll hear more about that when we talk about, well, the opposite of a real image is a virtual image, and a virtual image can't be projected onto a screen. So like when you look at something through a magnifying glass, that's not a real image. You can't project that image onto a screen. It's basically an image that your brain has kind of made up. Yeah, it's not actually there. I know, it's weird. Right. Let's just see if you can draw these diagrams for different situations. I want you to think that the object is moved to different places and just do what I've done. Draw one line from the top of the object, parallel to the principal axis and then down through the focus, and draw another line just from the top of the object straight through the centre of the lens as if nothing has happened. And have a think about what kind of image you've got. I think this is really difficult. I'm not expecting you to, and it's not a sign of intelligence, to be honest, whether you get it right or not. But I think it's important to give you a chance to just kind of play around with this so that it sticks in your head. So the thing to do is don't try and draw what you think you should be drawing. Literally just draw what ends up coming out as precise as you can. Here we go. So I've got this example here for you, a much nicer, neater example there. We said that our object was 2 focal points away from our lens. I drew one ray of light straight through, I drew one parallel to the principal axis and then going through the focus, and we end up with an image which was inverted, upside down, the same size as the object, one rectangle high, and it was real. So it appears where the rays actually meet and it can be projected on the screen. Can you please, if you have folded a piece of A4 paper in half 3 times, either way, can you draw the same sort of ray diagram for an object which is between 2 F and F? So just draw that little arrow on your piece of paper and then draw the rays and see what happens on the other side. Can you do it for one that is outside 2f, so further away than 2f? I've done it like a square and a bit. And can you do it for one which is actually on f as well? Make all your objects 1 square high. And then if you get time, if you're enjoying yourself, try one inside f as well and see what happens. So even closer to the lens than f. So your rules are a ray parallel to the axis always goes through the focus, and a ray going through the centre is not refracted at all. I'll do it with you, so I've got a rough idea of your timings. And you know what? I never say this. I never say this on Theatre of Science. But you should really use a ruler if you've got one. Shall I do I'll do a little thing just for people who are totally confused. If you've been following, great, you can just crack on. If you're sitting there like, oh, Lara, I went to get a snack and my dog sneezed and it was cute and I haven't been paying attention. What are we doing? I don't get it. Okay, this is for you. This type of lens is called a converging lens, right? It's like a magnifying glass lens. And what it does is, when light travels towards it in straight lines, the converging lens bends the light so they all meet at a point. They all converge at a point. And this F here, that's the focus, that's where they meet. So a ray of light travelling along up here is going to get bent by this converging lens so that it goes through F. A ray of light down here is going to get bent so that it travels through F, okay? So you end up, yeah, this is the focus of the lens, that's what that's called. If you put an object different distances away from this lens, then you get images appearing in different places. So what we're doing now is I want you to, this little arrow pointing upwards is the object. I want you to draw a little object which is between 2F and F first of all. So draw this arrow between 2F and F. F is where the light focus is, and 2F is just kind of something that we've made up to help us with this diagram here. It just means that's the focal length, the length between the lens and the focus, and that's just 2 focal lengths, right? So draw an arrow, an object, about 1.5 squares away from the lens, and then draw your ray diagram. So what a ray diagram is draw them 2 rays of light from the top of the object. One ray of light is going to travel just in a straight line, hit the lens, and then it's going to bend and go through the focus. That's what the first one always does. And the second one goes from the top of the object just in a straight line through the centre of the lens and out again, just like I've done here. And where the rays cross, that's where your image gets formed. So in this one here, we can see my image is upside down, so it's on the other side of the axis. It's the same size as the object, it's just 1 rectangle high. And we're saying that it's real as well, because it could be projected onto a screen. It's where some actual rays of light meet, but that'll mean more to you when we talk about images that aren't real, so don't worry about it too much yet. And then, yeah, when you've drawn your ray diagram, can you tell me, have a go at telling me, is the image that you've got, is it enlarged, so bigger, or is it the same size like mine was? Or is it smaller? Posh word for physics word for smaller is diminished. Is it upright or is it inverted? So this one was inverted, upside down. And is it real or is it virtual? But you, like I say, you might just have to guess at that until we go a little bit further. And if you've done that, if you're really happy with all of that, then the other thing you could be doing is thinking, why is this useful? Why would you want to position an object at these different places? Why would it be useful to have an image that is upside down and the same size as the object, or whatever you've got? So have a go at describing the image to me. I'll tell you what, I'll go through the first one, and then the people who haven't got a clue what they're doing will hopefully get a better idea of what they're doing. So let's go through the first one. If you put this object between 2F and F, what happens? Well, you draw, it doesn't matter which one you draw first, you draw a ray of light parallel to the principal axis and then going through the focus. And then you draw another ray of light which just goes straight through the centre of the lens and out again. So what image have we got there? Well, the image is formed where the lines cross. So you can see that this one is enlarged, right? It's bigger. It's bigger than the object. The object was one rectangle high and this one's a bit more. It's inverted again, just like mine was. It's upside down. And it's also real as well. It can be projected onto a screen. Why would that be useful? You might have to say that in your exam. Why would that be a helpful image? Why would you want to do that? It's very helpful. Super cool. In fact, if you saw the downstairs toilet activity we did at the start of the lesson, then that would be quite a cute clue, really. So the reason that I did the first one that I did first was because I got an image that was upside down and the same size as the object, and I have not really been able to find any use for that. There's some sort of copying machine from the 1800s that did that, but nowadays I can't think why you would want an image that was upside down, exactly the same size. But there's cinema screens in it, certainly old-fashioned cinema screens. The film goes in upside down, gets shone through a projector lens, and then that ends up really big on the screen, doesn't it? The right way up, because you've put it in upside down. See? Yeah, cinemas. Lenses are cool. I'll just give you a little bit longer to do 2, 3 and 4, and to think about what use these things would possibly be, and then we'll get going. So don't forget, don't try and force it. Don't try and do what you think is right. See what you actually get. Okay, should we go through it? Is that all right? It doesn't matter if you haven't got to the end at all, as long as you've got the vague idea. So yeah, the use of that one was a cinema projector. Okay, let's do number 2, outside of F. If you put an object outside of 2F, beg your pardon, more than 2 focal lengths away, what happens? Well, your first ray of light goes parallel to the principal axis and then through the focus, and the second one goes right the way through, and look, the image is formed where the lines cross. Oh, it's a little bitty image. Why would that be useful? We have an image which is diminished. It's much smaller than the object. It's inverted, it's upside down, it's real, it can be projected onto a screen. Why would that be useful? Come on, why? It's happening right now. It's happening to the vast majority of us right now. Any ideas? Yeah? It's your eye. Your eye, yes. It's a fairly well-known fact, isn't it, I think now, that the image that you see with your eyes. So you're looking at a tree, right? The tree, light from the tree goes into your eyes, and your eye is a convex converging lens. And this is what the situation is. The tree's quite far away, and you end up with a teeny tiny little image of a tree upside down on your retina. I feel like most people know now that the image that hits the back of your eye, your retina, is upside down. And it's your brain that flips it the right way around for you. So your brain sorts that out. Obviously, you don't want to be looking at a tree and have the image be the same size as the tree. That wouldn't it's not how biology works. So it's great that it's much smaller, and it is projected onto a screen because your retina, the back of your eye, is the screen. That's good, isn't it? So this is exactly what happens if you look at things with your eyes. Next one. At exactly F, what happens? Okay, so we've got a ray of light travelling parallel to the principal axis and then going through F. We've got another ray of light just going straight through. Oh, gasp. The lines don't meet. So we have no image, but that can be useful too. That's used for searchlights, that one. And we probably saw that, didn't we, in our downstairs toilet activity, or we certainly saw light travelling through the lens, but the rays not meeting behind it. I mean, maybe that was because they were just meeting somewhere that was too far away for it to hit my screen. But anyway, yes, searchlights. When sports teams are playing sports and you want to light them up, you would use something like that. And the last one, this is saved on YouTube, so don't worry if you think that I'm going too quickly. If you've got the printouts, you've got the answers actually. So inside F, what happens there? Okay, this is a bit weird. So we've got that ray of light travelling parallel to principal axis and through the focus. We've got the ray of light travelling straight. Oh, they're diverging. What's going on there? Well, there is an image formed in that situation. But it's not formed over here. Where is the image? Well, this is actually a magnifying glass setup. If you imagine that our eyes are here, seeing these rays of light, your eyes, your brain knows that light travels in straight lines. It has learned this from everyday experience. So your eye sees light coming from, well, it sees light travelling towards your eye, carrying the information of the top of this arrow, if you like, and it thinks, oh, okay, the top of that arrow must be somewhere along that line. So it extrapolates that information and thinks, okay, there must be a ray of light travelling in that direction, even though there actually isn't. And then it thinks, okay, right, I'm getting information about the top of the arrow, so it must be somewhere over there. And where those lines cross, that's the image. Isn't that amazing? So there you go. You do end up with an image that is enlarged, bigger. This time it's upright, and it's also virtual because you can't project that onto a screen. It's on the wrong side. That's the image that you get when you look at the magnifying glass. Good, isn't it? I wouldn't have expected you to get that. I just think if you've sweated over it for a while, then tends to help you remember it later. Okay, there is another type of lens that we haven't talked about. I prefer the name of this lens. So that lens was the convex lens. The other type of lens is called a concave lens. And I like it because I think it does kind of look like two little caves squished together. You can just imagine like a little bear hiding in one of those little caves. This is what's going through my head. Anyway, and concave lens, they're also called diverging lens. Wait, concave. I'm trying to write backwards whilst talking at the same time. Concave lenses are also called diverging lenses because you might have guessed what happens when light travels in straight lines into a diverging lens is that it gets sent off like that and it diverges away. You don't, even if you're doing the Cambridge exam, you're not going to need to draw a diagram of a diverging lens, but you do need to know how they work. So let's show you an image. It's just really cool. So here's our candle, here's our diverging lens. What happens is the same thing as usual. Light travelling from the top of the candle, say, through the middle of the lens just carries on in a straight line. This time, light travelling parallel to the principal axis. It goes off at that diverging angle. Can you see how you find out what angle it should go at? Like, why, if you were drawing that diagram, how would you know to draw it at exactly that angle and not like a bit steeper or a bit shallower? Can you see? It's because it actually, when you're drawing the diagram, it passes through the focus on the other side. So you don't really draw that ray of light because it doesn't exist, but that shows you what angle the light's getting refracted at. You see what I mean? So that ray of light goes like that and then gets diverged. But how the image happens is, once again, your brain imagines that there is a ray of light coming from that direction, and so the image ends up teeny tiny, like that. You see what I mean? So your eye is there, the candle's on the other side of the diverging lens, and yes, this diverging lens, it does that same trick to your brain and makes you see an image which is very small. Why would that be useful? Why would you want that to happen? Well, very quickly, before we go back to my downstairs toilet and enjoy the coolness once more. So you end up with an image which is diminished, smaller, the right way up, upright, and virtual, can't be projected onto a screen. Let's have a little quick exercise about how eyes work before we go back downstairs. This is the typical eye. This would be an eye that is working in the way that eyes work. Light travelling in straight lines, there's a convex lens in the eye which refracts the light so that the rays of light meet pretty much exactly at the back of the retina, and that's where the image is. Yeah, but it doesn't always work like that. So some people are nearsighted, or the posh word for that is myopia. Distant objects are blurry, and that can happen for a couple of reasons. It might be because the lens is very strong, so it's making the rays converge too early. So you can see this is why our image looked blurry downstairs when we moved it forwards and back again, because the lines weren't crossing on the screen. They might have been crossing too early. So that's going to look really blurry. Or the eye could maybe be very long as well. So the rays are converging in the sort of right place, but that's not where the screen is because the eye is long. And the opposite can happen as well. So if you're farsighted, then the rays are converging too late to hit the screen, either because the lens is weak or because the eye is short. And I've said this is what happens to a typical eye when objects get closer than 25 centimetres. So I hate doing it. It makes me feel incredibly uncomfortable. But if you move your finger very close to your eye, everything goes blurry. And it's because the rays of light they're meeting sort of, or they would be meeting past your retina, so your image isn't focused on the back of your eye. Okay, so very quickly then, just so we can say that we've done something to do with diverging lenses. Here you've got someone who's farsighted, so the rays are meeting too far back, and someone who's nearsighted, so the rays are meeting too close together. Which lens would you put in front of each of those eyes to help them see in focus? And if you've got the printout, or even if you haven't got the printout, it's not that hard to sketch, is it? Maybe you can sketch the right lens and show what actually happens to the rays of light. So one of those people is going to need a diverging lens in front of their eye, and the other person is going to need a converging lens in front of their eye. What do you reckon? You can answer just question one if you like, or you can answer both of them. I think sketching it would definitely help you understand him. But, I'm not the boss of you. You do what you like. Have you made your decision, even if you haven't sketched it out? That's a quite tricky sketch, actually, isn't it? All right, I'm going to show you. So this first one, the rays are meeting too far back, so they need to meet earlier. So we would want to put a converging lens in front of that ray of light. And if you were sketching this, say in an exam, you would have to show that the rays of light start converging once they've passed through that lens, so that the lens of the eye only has to converge them a little bit more to get them to focus on the back. And the other one would use a diverging lens because they need to be spread out for a little bit longer, don't they? So the rays of light would actually be slightly diverging when they hit that convex converging lens of the eye, so that the too powerful lens, or whatever it is, focuses the images at the back. Phew! Right, well done you lot. I think we should go downstairs now. Because I thought a nice end for the lesson would just be to do that awesome activity again, and also have a look at the images that I've got taped to my toilet wall to look at what is actually happening. Here we are again. Okay, so just going to light the candle. Don't forget, if you're enjoying these lessons, if you're enjoying the fact that all of the physics teacher training, what I have done, and the science degree that I've got are just being streamed live into the internet for you. You can pay me. It's literally the only way that anyone in my family makes money. Look how poor we are. Look at the state of my downstairs toilet. She says, I've got a downstairs toilet. That's pretty cool. Anyway, yeah, you can pay me for these lessons. That would be brilliant. You can sign up to support me on Coffee with £5 a month. Like I say, only way anyone in my family now makes money. Not our decision, but there you go. It's fine. Right. So, shut that door. So here we go. Here's the beautiful setup. I won't bother with, well, I won't bother with the magnifying glass. We all know what that looks like, don't we? Let's get to this gorgeous image over here and think about what is actually happening. So we were talking about moving the object various distances. I'm moving the magnifying glass because it's safer, and then I don't have to worry about moving the screen as well. So the first thing we did was we got that absolutely stunning upside down image of a candle there, didn't we? Stunning. Beautiful. So which one of these options is it? It's can you pick it out from here? We've ended up with an object which is big. I'll use the proper words. It's enlarged and it's inverted, it's upside down, and it can be projected onto a screen. So it must be this one, right? We've managed to position it so that our candle is just over one focal length away from our magnifying glass. Let's do the next one. Move it. Well, I'm saying move it closer. I suppose I should be saying we're going to increase the distance now between the object and the lens, aren't we? We're increasing the distance. So there it's gone all blurry. So hopefully now you kind of know what's happening, right? Is that the rays of light just don't happen to be meeting on the screen. So we're not getting an in focus image. Oh, it's so diminished, isn't it? It's so cute. So what have we got there? It's diminished, it's small, it's inverted. It's definitely real, isn't it? It can definitely be projected onto a screen. So which one of these is it? It's teeny tiny. There we go. It's that one. It's behaving in the same way that our eye is, isn't it? So look, the diagram that we drew was correct. When you move the candle really far away from the lens, you do get this small upside. Oh, physics works. It's amazing, isn't it? And then obviously the last one, which is kind of obvious, is you look at something through a magnifying glass, and you do. It's weird because obviously it looks like the thing, but it must be an image. It is an image, isn't it? Because it's not the real thing, and it's bigger, and it's the right way up. So it's this one. It's bigger, it's the right way up, and it's not real, it's virtual. All right, you lot. Okay, I'm going to go. I'm going to blow the candle out as well for safety reasons. Thank you so much for joining me. Yeah, if you want to support me, then, I suppose, actually, I better go upstairs, hadn't I, and see if there's any comments. Oh, it has. Yeah, I will, very quickly. Yeah, if you want to support me, what a great ad. Just in darkness. Go to my About section and sign up to send me £5 per month, which I think actually, I never really say this because it sounds a bit cocky, I think £5 a month for these lessons is amazing value. You lot get the best value. I do teach all ages lessons as well, which are really fun. I love them, and they're the ones that most people come to. But these are the ones where I am actually using my physics teacher training, which is, reasonably hard to come by. So yeah, if you think that £5 is good value for a free physics lesson, well, not free, is it, if you're paying £5 a month? You know what I mean. If you think that it's reasonable to pay £5 a month for physics lessons online, where I say take comments at the end and there are free printouts, then please go to my About section and sign up, and I will be so absolutely, totally delighted. It'd be amazing. And I'll send you nice stuff to say thank you. I'll send you Theatre of Science magazine. Oh, I've got a few comments. Lovely. Oh, Bastian's here. Yay. Hello, Bastian. All right. Who else is here? Oh, Olivia's here. Hello, Olivia. Yeah, sorry. Well done for sticking with it, you lot. Hello, Jacob. All right. Wow. Is that your house? That's awesome. The colours. Just nosing. Oh, no, it's not your house. It's a cafe. Wow, that's a nice looking cat. Is that a cat on your... You guys get to some cool places, don't you? Blooming heck. What the deuce is going on there? I am back. Edmund. Oh, Edmund, you stuck with it. Thank you so much, Edmund. Oh, that was... It's not your problem. It's so annoying when that happens on YouTube. It's so annoying because they're supposed to be saved forever, right, on YouTube for watching on catch-up. And that's just a massive amount of hassle now to try and get those two videos and collect them together. You know I'm not going to get around to it. Hello, Freya. We found the new start a few minutes late. Oh yeah, that's okay. I kept worrying that people were going to turn up and think, oh, she must have started ages ago, but you hadn't really missed anything. Hello, Neve. Hello, good to see you. Oh, thanks for sticking with it. That's very nice. Right, yes, I am going to go. So next week we've got, I think we're doing diffraction. So if you sign up to support me, one of the things I send you, as well as Theatre Science Magazine, is some diffraction glasses that make you see rainbows. Yeah, there's a good activity with brilliant. Okay, yeah, we'll do diffraction next week. And we'll be doing waves right up until, for the next, well, now I've done this one, the next 6 weeks before the summer holidays, and then we'll start something else after the summer holidays. Okay, thank you so much for joining me. Thank you so much for all your support. I will see you next week for a whole new load of lessons. Just one more comment. Let's see who's commented. And then I'll go. Honestly, I will. Xavier! All right. Xavier says hi, and that the mystery plant from No Mo May is Speedwell. Thank you. Thank you. Yes. Thank you so much. Love it. Brilliant. It's still in my garden, so I'm going to go and have a look at it. Yeah, thank you so much for coming. I'll see you all very soon. Bye.